NTU World of Wisdom. Welcome to High Impact Thesis. In this podcast, we speak with researchers from various scientific fields to talk about the motivation, goal, and potential impact of their research. We also want to give you a sense of how a Ph.D. is carried out with an emphasis on the PH, the philosophical aspects involved in pursuing a Ph.D. Hello everybody, welcome to the High Impact Thesis podcast. Today our guest is Mr. Bernardo Noronha. Welcome to the High Impact Thesis, Bernardo.
Hi, thanks a lot for having me here.
You're most welcome. So as usual on this podcast, the structure of the conversation is that at the beginning we'll talk generally about what Bernardo is doing. And then in the second segment, we're going to talk very specifically about what he does in the lab, his day-to-day kind of work, and what tools he uses. The third part is going to be more philosophical, we hope, whereby we want to look at his work in general. What is the long-term agenda for his field, right? And then finally, we're going to talk about his personal interests as a human being besides doing the research that he's doing. Okay, so to get us started, Bernardo, if someone were to ask you, what do you do? What is the short version of it that you give them?
So I'm working with wearable robotics. So it's a subfield of robotics. I guess a layman, if they're told about robotics, they'll think of maybe industrial robots, so stuff that's used for assemblies in factories, or these big, clunky, futuristic looking robots.
Yeah.
I am not really working with that kind of stuff, but more with robots that are meant to be worn by users. So maybe the word that you're more familiar with is exoskeletons.
Okay.
So a little bit like what Iron Man is, but that's a very fantasized version.
Okay. So I suppose this is flexible stuff since it is wearable.
Yeah. Actually, that's where the field is heading towards now. But originally, they weren't really like that. They were more like Iron Man. So they used to be more like at least the very first iterations or attempts at having such a thing as an exoskeleton was just huge device that you can jump in, right? So it's like it's literally like a humanoid that you go inside it.
Okay.
I don't know if you've seen The Matrix. They have similar robots to that. So that was like one of the very first versions of these robots. But obviously, it's not really usable. And they were actually meant originally for military, but I am not really interested in that side, more on the how can we help people that cannot really move well. They have some disability. So, for example, stroke patients, it's a huge target of such devices. So they cannot perform the normal functions of their arms or their legs. They cannot lift their arms. They cannot walk properly. And how can we use these robots instead of using a therapist to help them perform these functions?
So these are kinds of robots that, like you were mentioning about those in the factory, they're like independent, but these ones work naturally with humans, I suppose.
Yeah. They actually, it's you have to take into consideration specifically that, and that's a huge part of it, because you cannot hope that the robot won't hurt the human, because it will hurt the human if it's not properly designed. If it's not properly controlled. So but going back to what you said about being flexible, so I mentioned that originally they were more on the rigid side, which means that they're made of these rigid components like steel or aluminium, maybe if you want it to be lighter, or plastic even. But the problem with those robots is that there's a higher chance that they will hurt or at least create some sort of uncomfortable positions for the user, because the way that the robot moves is not exactly the same as the arm or the leg. So you want to be sure that whatever inconsistencies there are, whatever misalignments between the robot and the human, you want them to not hurt the human, and you don't want the human to feel like this is a weird thing that I'm using, and this is not behaving as it should. And that's where these flexible or soft sort of devices come into play. Because whatever sort of misalignment there is, it just naturally is compensated by the fact that the robot is not forcing you to go to a certain position. It's more like a suggestion.
Okay.
So yeah.
So you have to program it in such a way that it knows, I shouldn't force myself, but it also is supposed to listen, right?
Yeah. It's you could say that's on the more engineering side of it, that you're adding a certain compliance to the device. So if you don't have compliance, then you're gonna have very tricky situations. And of course there are advantages and disadvantages, right? If you have a rigid robot, you know exactly what it's going to do. You know that you give it a certain command and for sure it's going to reach a certain state. But if you're dealing with soft robots, so if you introduce compliance, then you're accounting for any sort of like I said, misalignment or any sort of unpredictability that comes from the very nature of human robot interaction. And that also introduces challenges because it's more difficult to know exactly what is the robot going to make the user do. Yeah.
So any personal story as to how you got here, how you got into this area?
Yeah, so originally I wanted to study medicine because I've always been more interested on the human side of things, like how to help people, how to care for people. I didn't really want to have a job that there's the chance that I'm not going to be interacting with people. But my grades didn't allow me to do it. At least in Portugal, it's quite difficult to get accepted into medicine. But I was not that sad because I applied for biomedical engineering, which was a bit of a trade-off between what I really wanted to do in terms of when it comes to interact with people, but also on what my, let's say, intellectual interests were, which was more on the math side, physics, all that. So I found that this was the perfect middle ground between a doctor and an engineer. I'm basically supporting doctors with devices that will hopefully help people that have problems, disabilities, all that.
Okay.
Yeah.
So then in the biomedical field, you decided to focus on robotics.
Yeah, I decided to focus on robotics because I feel that that's where the more engineering challenges or the higher engineering challenges lie. I could have gone for other stuff like, I don't know, drug delivery systems, or maybe on the more management side, right? So understanding how health systems work, how should you organize a hospital, those were all possible scenarios. But I felt honestly like my interest just lied on the more engineering side of things. And not only with biomechanics, because that's at the very core of what we do, right? Understanding how the human body moves, but also how can we support that function of the human body. So, and that's where the engineering comes into play. You need to understand what kind of sensors can we integrate in the body. I don't mean inside the body, but that's also a big part of it, obviously. I don't deal with that though. And also how does the body, how do you actually perform certain movements? Like how does the brain decide, oh, I'm going to move my arm in this specific manner and not in this other manner? How do all these things work? It's also at the very basis of how can we, in helping design these robots, right? Because you need to understand what's a natural movement and how can we simulate that movement in a robot. Because actually that's also one of the big challenges, which is to, I'm sure you've heard of it, the inverse kinematics problem, right? So let's say if you want to reach with your arm a certain point on the table, where the final point is, and you even know that usually we perform a certain kind of trajectory, which is a straight line, high acceleration in the beginning, and then small acceleration at the end. But how does the rest of the arm move? That's a huge problem, because you can literally have infinite types of ways of how you can configure your arm. And people still don't really know how does the brain decide how to do it. There are many theories, people devise like these cost functions, try to understand, if the arm is in a certain position, your body spends more energy, so we should reduce the energy. Or some other theories say that the brain already has programmed a few types of ways to move, and it just saves, let's say, computation cost by just falling back to what's already there. So all these things are extremely interesting, and they are part of what I've had to understand, study, so that we can then replicate this with robots.
Right. No, that's definitely interesting, because in the process of being an engineer, you have to understand the human. So I think that your research is interesting because it's both human oriented as well as an engineer in that sense. Very exciting stuff.
All right, so I guess you gave us like a good idea on what do you do in general, like what's your domain, let's say. But now we'd like to get a little bit more into the details, into the specifics. So let's start with the whole design of the robot, right? Is that something also you're involved on, like the physical design?
Yeah, it definitely is. Actually, that's the thing that I've been working the most in, which is the actual mechanical design of it. I think generally people would think that it's kind of an old field almost, right? So nowadays everybody's very turned towards like AI, computer science, software. But there are still so many interesting things that you can do with mechanical design of these kinds of devices. So we mentioned before that you have like these rigid robots, you have these soft robots. That's all part of the design. Mm-hmm. And the thing that I've been focusing more on is on what I call hybrid robots. So it's neither fully rigid, neither fully soft. It's a mix. And this is quite a recent field. So you could say that it has been around for some time, but people only started calling it hybrid robots more recently. And the nice thing about this is that you can leverage the properties of rigid robots with the properties of soft robots. So typically rigid robots will have higher power output. It's also more easily controlled, so you know more precisely what it does. And soft robots, like we mentioned, they have higher compliance, so they're safer to use generally. And people prefer soft robots because they also don't look as ugly as the other ones.
What's an example of a soft robot?
So a soft robot can be, for example, just wires that you attach to certain segments of your body, and then you pull on those wires almost like a puppet. But the wires go very closely to the arm. So, to the arm, any part of your body really. If you imagine, for example, a glove, right? And you have wires that are woven in the glove itself and then attached, for example, to the fingertips. If you put the wires on the dorsal side, meaning the back of the hand, when you pull the wire, you're going to open your hand. And then if you put the wires on the other side of the hand, so on the palm side, and again, you attach them to the fingertip, if you pull the wire, then you're going to close your hand. And you don't actually have to see the robot because it's like a glove, basically, with these wires that go through it. So people, in general, these robots, they are quite more accepted because they are more disguised. So actually, the term that it's used a lot is exosuit. It's not even really robot or exoskeleton. Now, exoskeleton refers more to rigid robots. So what I started to try to do is let's try to not only use the soft properties, so for example using wires, right, but also try to add some rigid elements there, because one of the problems that you'll have with soft robots is, so let's take back the case of the hand, right? If you attach it to the fingertip, you don't really know exactly how your finger is going to close. You just know that your finger will close, and you hope that it will be in a nice way, that you want it to work well. The nice thing about hybrid robots is that you can use the properties of the rigid components to prevent certain motions, for example, from happening. So if you attach a wire to the back of your finger at the fingertip and you pull it, your finger, most likely what's going to happen is that the tip of the finger is going to go back, but the other part of the finger, it won't really move that much. So all of the force is being applied to the tip of the finger. So if you have quite a strong pulling force, it means that you can have all of that concentrated on one single segment around one single joint. And that's not desirable because you end up doing a natural movement. But if you decide to put rigid elements there, like blocks, for example, on the back of your finger, you can prevent that unnatural movement from happening because you have something rigid there. It does not allow you to do that kind of movement. So you can use these sorts of properties to better support function. Other ways that it can be used is, so still on the cable-based kind of robots, what ends up happening a lot is that as the wires are pulled, the robot rotates, so the glove or the arm exosuit that you're wearing, it ends up rotating around the limb itself. This will be, just imagine you have a shirt, right, or a glove. If you start pulling the shirt in different directions, the shirt rotates around your body, or the glove rotates around your hand. So inevitably, you will have a shift of the forces that you're supporting to the body, and you might end up with a configuration of the exosuit on your body that is not aligned with the function that you're trying to support. So let's say you have the wire, instead of being on the back of the finger, it's on the side of the finger. That could happen because it's a soft robot, it's something that's meant to be worn. Then what's the point of even having the robot if it's not going to be performing as it should?
Right.
So that's where you also introduce some sort of, for example, more rigid components. So you can have like bars across certain parts of this exosuit itself, rigid bars that prevent it from rotating. That was one of the very first hybrid robots that came along, where this research group, they literally just put like a steel, or, well, maybe not steel, but a metal bar across the palm, and that prevents the glove from moving all around the palm because you have this bar there that will simply not move as opposed to the rest of the robot. So these kinds of things are very much mechanical design, and it's still super interesting because you can actually relieve a lot of the computational cost that usually is associated with these kind of complicated devices. Right. And you can embed all of this intelligence, let's say, on the robot itself. So by designing the robot in a certain way that it does not allow you to perform certain movements that are unwanted, you don't have to worry in the control itself about these potentially undesirable situations. So you simplify the software by choosing smartly what are the mechanical components that you're going to be using. That's called embedded intelligence. It's also quite a hot topic nowadays. Simplify the control by embedding all of these little details on the design itself of the robot.
So a mechanical kind of computation.
Yeah.
You kind of know the answers beforehand, but you put them in. Nice. Okay.
Yes,
or
exactly.
Or kind of limiting the space of variables somehow. Yeah.
Yes, it's exactly that. It sounds very fancy, but this is something that people have been doing since thousands of years ago, right?
Right.
I can't exactly tell you an example from thousands of years ago, but if you just think of a car like with a suspension, right? That's pretty much embedded intelligence right there. You could have thought of it as, okay, let's put an actuator that whenever the car goes over a hump, for example, the actuator pulls the wheels up, and then when the hump is gone, it pulls the wheels back down. That's a lot of effort that can just be achieved with put a suspension thing there. put a dampener there.
Yeah.
You don't no longer have to worry about these things. It will always work because it's mechanically there.
There's a channel like King Mechanical on YouTube, right? And this guy has a lot of a lot of machines like showing mechanical movements, and you have these machines that they would definitely have an Arduino or something like that. Like they're like paper sorting machines or cutting machines that are very precise, but it's all mechanical. You just design it so that this is what it would do no matter what once you move it this way. So I think this is quite interesting because I think in today's world it's more like software. Let's do it, since we can. So it's nice. You're going from the other direction.
The idea of hybrid robots, it kind of strikes me like an attempt to mimic nature, right? With like having bones and muscles and all the fibers and the strings pulling on the muscles on the bones.
Yeah, it's exactly that. Actually, we are in a sense hybrid devices, right? It's what you said. You have the skin and the muscle that's very soft, so it softens any sort of impact that you could have. It's also protecting the bones, and then you have the bones that are the hard part that takes the actual impact, the forces. It's designed that way. Actually, your bone cannot live if it's not under impact. And that's in a way what we try to mimic in these robots. But it is it's hard to say whether this is the best direction possible or not. I mean, nature has designed it that way with us, right, with the bones and the skin. But we are not, what I'm designing is not a prosthetic device, right? So in a prosthetic device, you could say if you want to mimic nature, then you would definitely need something that's hard in the center and then soft on the sides. But that's very different from what we're working with, which are devices that you wear. It goes around your body. So in some scenarios, I guess, you don't even really need a hybrid. In some scenarios, maybe it's better rigid. Some scenarios, it's better soft. But I have found that actually most research groups worldwide, they are focusing a lot on soft or hybrid. Actually, soft robots are a big thing nowadays. Hybrid, it's up and coming, so it's something that only really started like 3 or 4 years ago, more properly. But yeah, it's definitely a very interesting way of looking at it. Yeah, I've seen also other ones that they call, for example, lobster-inspired soft robots, where it's the opposite. You have a soft inside, so it's like a bladder that you fill up with air, and then on the outside it's a rigid like shell. So as you fill up the bladder, depending on how you design the outside, the whole structure bends with a certain in a certain shape, like a lobster really, or like a shrimp, and you can use that, for example, on the back of your fingers. So as you inflate these bladders, these structures rotate and it forces your hand to close. Another way of doing that is just forget about the shells. Just use the soft devices. You don't need the shell itself. But then, again, you might encounter some problems with undesired motions. All that.
Okay, now what about the other half of the design, which is the software part? How do you deal with that?
Software is, I'd say, it's probably the biggest challenge. Maybe that's
because what you do sounds very complicated. You're dealing with a lot of moving parts and.
Yeah, I am actually. So I haven't dedicated that much time to the software itself, because honestly, you could have many PhDs on just that,
Right.
But you can break it down as that. So the software, you can break it down in how do you control the robot in terms of how do you decide how the robot itself moves. So how do you decide, okay, like if you have a cable-based robot, right, with many cables, each cable attached to an actuator, how do you decide how much do you rotate a certain actuator, how much you pull a certain cable, how much do you let go of another cable? So that's on the more control of the device itself. But then you have on the other side, how do you give those commands, right? So how does the human decide, or how does the robot understand what the human wants to do? And that is a very difficult problem to solve. And the main reason why it's so difficult, it's because you're dealing with, at least in my field, right? You're dealing with people that inherently their body has some sort of disability. So if you are relying on a body that has a disability to control a certain robot, you are going to encounter problems. So let me just explain that a little bit better. So for example, in stroke patients, which are probably the biggest target group for these kinds of robots, you have a person that has had a problem in the brain, right? Part of their brain has been lesioned, might even be dead. They might not be able to recover certain function of the brain. So fundamentally what happens is that they lose ability. And generally the way that people see this is either in the drooping of the mouth, right? Or the it's usually only one half of the body, or the hand, they can no longer use the hand and the arm correctly. So you'll see many people, when they try to use their affected side, they'll just end up like curling up the arm around itself, and they use a lot of the big muscles in the body. So they can no longer control the fine muscles. They can no longer open, like they couldn't play the piano, that's for sure. They might still be able to lift their whole arm, but they cannot have the fine motor control. And this all comes, it's not because there's any problem in the muscles. The muscles are fine, right? The muscles can still, they're as healthy as any other person's muscles, at least at the very onset of the stroke. The problem is that their brain can no longer control those muscles. So you have this perfectly fine tool, which are the muscles, that can be used, but you don't have a way to control them. And just like with almost everything in your body, if you stop using it, it just stops being as good. That's why we work out, right? So if you stop using those muscles, then you start having problems with those muscles. They atrophy, and you eventually lose a lot of muscle mass. So you can now try to control the muscles directly, but it's difficult because the muscles themselves, they are not as good as they used to be. So
could you explain just a little bit on this one? So when you have your robot, right, and you want to talk to it, you've just mentioned that stroke patients might have an issue because their brain is not able to send the right commands. So I'm wondering whether normally do you talk to it with the brain, or do you like get the signals from the muscle somewhere already? As in, I've already made the commands in my head, and then I'm not able to execute. What is the more common, or what is the more common implementation of this? Is it talking from the brain, or you take it from somewhere else outside already after the brain has sent the command to the body?
There is no more common because there is no sure, like, fail-proof way.
Okay.
So there's not, to my knowledge, to the best of my knowledge, there's no commercial device out there that stroke patients can actually go around and use. So something that they can use in their everyday life, right? There's nothing like that. There are devices that can be used, but they will be mostly used by healthy users, and that will be in scenarios like military scenario, right? Or a lot of these robots are also used in industrial settings. So to help in like moving stuff in a warehouse. So those two scenarios are very, very different from the stroke patient, because in those cases you can decide to use whatever you want. Brain waves, you can use directly the muscle signal, which is called the electromyographic signal. So you can just capture that with sensors and amplify it and use it to control the robot. Right. But with a stroke patient, it becomes quite difficult because those signals are not there on the muscle. And if they are going to be damaged. So that's actually, I would say it's one of the biggest problems right now, because a lot of the devices that we develop, and that we as the research community, right, it's based on the assumption that they'll be used with, for example, electromyographic signals, right? So the electricity that comes from the muscles. And you'll see like so many devices are controlled using that. But then the stroke patient cannot use it because they don't have those signals. So what's the point of testing it with those signals? There's a huge mismatch between what actually needs to be done and what's being done right now.
But I get the complexity of it, because if there is no brain, then it's like, how do you even talk to your robot? Because at first
what's the alternative here? What's the solution?
No, but you can use the brain because the brain is more capable than the muscles, right? The brain has this thing called, this property called neuroplasticity, which means that if a certain part of your brain gets damaged, other parts are going to take over.
Oh, right.
So this traditional idea that certain areas of your brain are dedicated only to that, and if they die, you lose that forever, it's not really, really like that. In truth, surrounding areas are going to take over the functions of that area. So you know that your brain can adapt to any sort of, not any, but it can adapt to many lesions that it suffers. So you can use the brain. In truth, it's the more fail-proof way of going about it. The problem is it's quite difficult to access the brain. So if you want to access it from the outside in a non-invasive way, then you are already limited because the signal is not going to be very strong. You're going to have to deal with stuff like the most basic of things like hair. You need to deal with the hair that you have on your head. You might have to shave your head in order to get proper signal acquisition. But that's, I think, a more, let's say, a minor concern, right? The real problem is that the signal in general is very noisy when it comes to these non-invasive ways of detecting those robots. Detecting signals. And another thing that, again, we as researchers forget to consider is that what if the user does not want to have this ugly thing around their head to control a robot, right? Many users are just going to say, I might as well not use my arm for the rest of my life. It's true, they are fine with that. They would rather have an impaired arm function than be seen with this horrible looking thing on their head all the time. So there are other ways of doing it, which is the more invasive way, right? So you put something inside your brain. That's obviously not as well accepted because in general,
what Elon Musk is trying to do, right? With Neuralink.
Exactly. Yeah. You have Elon Musk with Neuralink. I saw a seminar, I think 2 or 3 years ago before the pandemic here by this professor, and it was fascinating. They had developed this sensor that it was basically like Neuralink just before Neuralink. And it's, I mean, of course it opens a lot of possibilities, right? Because now you have direct access to the maestro of your body. You can just talk directly to the brain, or you can listen directly from the brain and send signals to the robots. But it's still, I think we're still a little bit far from actually controlling these robots with, or to have a widespread distribution of these sensors. So maybe in 10 years, you'll have that as being something that the doctor will propose to the patient. Hey, look, we can put this thing in your brain, and then you'll have this robot that looks like a normal sweatshirt, and it will just help you in performing movements that you can no longer do. I take that back. Not 10 years, probably more like 50 years.
Wait, so help me understand. When you talk about invasive, for example, you have this device in the brain that decodes the brain signals, right? Mm-hmm. How do you get them out? Is it Wi-Fi, or like is it actual wires to the actual the robot? Or how do you get the signal out of the brain? Or is it? That's what I'm wondering. They have to open up the whole body the same way that there are sensory neurons in our body, or?
No, yeah, that's a great question. I'm going to be honest with you. I'm not super well versed in brain signal acquisition.
Okay.
Especially in the invasive kind. I know non-invasive, it's, well, you can either go wired or wireless, right? It's quite easy if you can just have a cable connected to something that's attached to your skull on the outside, right? But when it comes to invasive style, it's mostly wireless, I'd say. The ones that I've seen are all wireless, which is also one of the challenges, right? You have this thick skull between your sensor and whatever it is that you're trying to, whatever it is, the receptor of those signals. And you have to have it to be very small. You have to fit in there a battery, an integrated circuit, right? So you have to have sensors, you have to have so many different things. And where do you even place it in the brain? Do you place it in the middle of the brain? Do you place it on the outside layer, right? So between the brain and the skull? And how many sensors do you even put? Because if you put it on one side, you're going to be limited to the signals around that area. What happens to all the signals on the other side? So if you're dealing with a robot, right, you might want to put it on the side where the motor cortex is, right? The part of the brain that's responsible for sending movement to your limbs. But then if you want to help, for example, with other functions, then you might not really need that sensor anymore. You might need other stuff. So it becomes, I mean, it's a deep well, right? There are a lot of things still to consider there. And that's why I say that it's not really there yet, at least not at the commercial level when it comes to using this for controlling assistive devices. Which is why a lot of these things end up not really being used in a practical scenario, and you end up using very basic ways of controlling these robots, like a joystick or like an Xbox controller almost.
Is that what you use in the lab currently?
I have been using mostly that, yeah, like switches, buttons, or you have the robot attached to the computer, connect to the computer, and just on the computer itself you can send signals. Right. Again, that's on a more low level of development kind of thing, right? And it also depends, because that's also a huge thing that you need to consider, which is, do you want this robot to be used by people on their daily life, or do you want it to be used in a rehabilitation scenario? Because you have a lot of robots used in rehab clinics, in hospitals, that are meant to be used just there. They're meant to be used with somebody helping the patient use that robot. But when you want to then send that robot home so that it can help the patient home, that's a whole different scenario. You'll see that the number of robots that you have that are meant for clinic use is many, many times higher than the number of robots that you can actually use at home for these scenarios, right? I don't mean like social robots or something like that. I mean robots that you are meant to wear, robots that are certified that they're not going to hurt you, they're not going to break your arm, they're not going to create rashes on your body, and on top of all that, they will actually help you. Because that's also another thing that many people talk about, which is this actually helpful? Like, at the end of the day, do we want to use these robots, or is it just simpler to go on with my life, learn my strategies around my disability, and just live with that? For a lot of people, it's like that.
I think there are also financial considerations, right? Because usually these robots are extremely expensive.
Yeah, definitely. I find it a bit paradoxical almost, because definitely one of the reasons why people don't use more of this, at least for personal use, is cost. Right? You have a few robots that are certified to be used in home scenarios, and I don't mean wearable robotics. I mean just rehabilitation robots. So things like, for example, you hold a manipulator, like a stick, and that stick is attached to a platform that moves the stick around, so it helps you in performing certain movements. So let's say you have this robot on the table, right? You grab the stick and then the stick moves around. What I just described to you is actually a product from a spin-off here at NTU, which is one of the biggest things I think to come out of my lab, the Robotics Research Centre. And it's also one of the very first robots to be certified like that. And it showed, this is a very recent company, so this is something that was only put out there, I mean, in the last 2 or 3 years, right?
Mhm.
So we've heard about robots for many years, and only now are you actually having all of these things being certified to be used at home. So it just shows how much of a gap there is between research and actually like usable products out of there. So it is very expensive to acquire these robots. But on the other hand, one of the arguments that is usually given for the use of robots is that in the long term, it makes it cheaper.
Mm.
Right? So there's a large investment that needs to be done at the beginning, because some of these robots will cost $300,000, right? But in that case, they'll mostly stay in the rehab clinic because they can reuse it many times, different patients, many years. But then at home, that becomes it's very difficult. I mean, unless you're rich, you cannot be spending $500,000 on a robot to have at home. It's just, why would you do that rather than have a therapist visit you, I don't know, 2 times a week and help you do those exact movements, right?
Right.
That's the big thing there.
Okay.
So the robots that are certified for home use are simpler and easier to work with than the ones at the clinic, or is the reason that there are fewer in homes now the cost? You get my question? Is it the cost, or is it the fact that the ones at the clinic are kind of not simplified, but the clinicians kind of understand, while it's at home, it would take a lot more time training them. What is the reason for having fewer at home than in the clinics these days?
I don't know for sure, but I think it's related to what you're mentioning, that robots for home use are simpler. So you want to have something, it's like an appliance, right? You don't want to have to worry about learning how to use it. I mean, even if you buy a vacuum cleaner, right? You know pretty well how it's going to use. If you've never seen a vacuum cleaner before, you will still be able to understand how to use it, right? Press a button here, sucks air out of there, point it to the floor. It's not very difficult. It should be the same with a robot. You shouldn't have to study how the robot works in order to be able to use it that much. And the ones that you see being used at home, they're generally the very simple ones. So the one that I was telling you about it's literally something that you put on a table. It looks like just a box, and then you just grab this thing on the box, and this thing that you grab, it just moves around on top of that box, so it helps you perform planar movements. And this is one of the most common types of rehabilitation that you have for stroke patients and people with other sorts of neurodegenerative diseases. And then another big thing that comes to change the way robots are used is the gamification of this whole process. Because if you give the user, the patient, a robot without a real purpose of what to do and without any sort of motivation for using it other than you need it to get better, it's different from, hey, you can use this robot to play a video game. People get way more excited about that. And there's a lot of research on this going on as well, about how does gaming change the perception of these robots by the users.
So you mean the gamification of the learning to work with the robot, or just that you will be able to use it for games?
Oh, no. I mean the gamification of of the rehabilitation process.
Okay.
So let's say that you have a certain exercise that you want the patient to do. And that exercise is just moving your arm left, right, left, right, left, right. Right? So let's say you have a cup on the table. You grab that cup and you put it on the left and then on the right and then on the left. You just do that many, many times. This is boring, right? People get tired of doing this. Yeah. But let's say now you have this attached to an interface that shows you on the screen that you are actually controlling a spaceship. And you need to go through certain hoops. So you need to be able to control the ship by going left and right. And now you're challenged because you want to score the highest score possible. You want to beat yourself. Maybe you want to beat other patients that are using the robot somewhere else around the world. And you're doing exactly the same exercise, but your motivation is completely different. Not only will you be more engaged, but you will probably also have better outcomes. Because you're putting more effort into it. And
that's quite nice.
Yeah, that's one of the main reasons also why I think these robots, it's interesting to have this at home use, because you just make it more interesting for the patients to use it. You create a need for them, not a need, but you create a want to do the rehab, rather than having to go all the way to the clinic, spend 1 hour going, 1 hour coming back. It's very costly also. I mean, of course it's still costly if you just have a robot, but hopefully in the future it's not going to be like that, and everything indicates that it's moving in that direction, that it will become cheaper and cheaper.
Okay, before we move on further, we always like to give our listeners a glimpse of your daily activities in the lab, like the tools you use, the machines, the software, and all of that. If you just can give us an idea of what is the most commonly used tools in your area.
So I there's not a day that goes by that I don't use MATLAB.
Of course.
Yeah, so MATLAB, a lot of MATLAB. Simulink, which is the part of MATLAB that it's more concerned with this, with simulations, and can use it in real time to control robots, and there are a lot of libraries available, a lot of functions. Maybe some of the people that listen to this will think, wow, Simulink, that's quite outdated. But the truth is it's very easy to use and very widely available if you have the money, obviously, because MATLAB is not free.
Wait, is it those tools also an Octave then? The one that's like MATLAB cousin?
I don't think so.
No,
I think Simulink is not on Octave, but I'm not sure.
Okay.
But you can also just decide to go more, let's say, low-level kind of programming where you just use like C++ or something like that, right? You will be coding your robots using that. But a lot of the things that I use will be sensors. So I haven't really worked on creating my own sensors because there's just so many options out there. So what I've used a lot will be EMG sensors, which are the ones that detect the muscle activity. Then we will also be using IMUs, which are sensors that are able to tell where are you in space, what's the orientation. So, for example, every smartphone nowadays has an IMU.
Inertial measurement unit.
Exactly. Thank you.
For the younger listeners of the show.
Yeah. So you can use those as well to help you in controlling your robot better, because you might be able to tell, this person's arm is in this certain position, which means that the robot needs to move the elbow by a certain amount in order to achieve the goal, right? You use these sensors to just be able to tell where in space are you.
Right.
What else do I use? Also a lot of just mechanical tools. I've been doing a lot of 3D printing. So 3D print like the rigid parts of the robot that I was mentioning. I do both like rigid, as in hard parts that are not flexible. But I've also done a bit of 3D printing of flexible parts with the TPU. I'm not sure what it stands for, but it's a flexible polymer that it gives that flexibility, that compliance to the robot, right? What else? Well, this you can.
Do you have some motors? What kind of motors? Do you
Of
use?
course, yeah, motors,
Actuators,
yeah. So you can use your typical motors that you see in all of these like robotics applications, right? So DC motors. You also have stepper motors, but those will be used more in rigid devices. If you're using soft devices, so you can use, for example, the motor attached to a wire. So that you have the motor, you have the shaft of the motor that rotates. You can attach a pulley or a spool, however you want to call it, to the shaft of the motor, and then you attach a cable to that pulley or spool. And as you rotate the shaft, the wire is wound around that spool, and that's how you create motion on the wire. That's how you apply a force with the wire. Or you can also use, I haven't been using that, but I'm also familiar with it. You can use fluidic actuators, or so pneumatic or hydraulics. Hydraulics, actually, there's only one device that I've heard of that uses it. When it comes to soft devices, the world is torn between pneumatics and cable-based actuation. So the pneumatic one would be, you have a compressor attached, and then you have tubes attached to that compressor. The tubes will be attached to bladders that are placed on the distal parts of your body, or wherever you want the actual actuation to occur. Right? So you might have those bladders on the back of the fingers, and then you just inflate the bladder, and that's it. The thing with that is that generally they're quite loud, these compressors. Right. They're bulky, they're heavy. I've seen one device by a group in Harvard. They're one of the groups that's leading the field. That they have done a portable device that uses pneumatic actuation. They are very strong in the pneumatic actuation part. I am not really sure how actually it fares, but other than that, I've never seen a device that's portable that can be used like that. So you'll need some sort of you'll need to be fixed to a certain workspace, because you cannot. Those things are heavy, man. Yeah. What else? The way to deliver the cable-based actuation is actually using something that you're very familiar with, which is Bowden cables. It might sound fancy, but it's literally just the brake cables on your bicycles. You know how you have those sheaths?
Okay. Yes.
So the wire goes through that sheath, and then you can deliver the tension in the wire to any place you want. So that's how you achieve remote actuation. Instead of having the motor directly on your body, which is also a possibility, but usually those are more, prototypes, right? It's something that's still on a very research-based level, not so much on the commercial side. But yeah, you can have the motors directly attached to your limbs. But most likely you will want to place them remotely, because motors are heavy and they create undesired, motors are heavy and they're bulky, and it means that you also will have to be withstanding the weight of the motor and make sure that it doesn't crash with anything in your environment.
And the vibrations
The vibrations, exactly. It's not very nice to look at, That's always a big concern, aesthetics. So you will want to have it placed remotely, and that you use Bowden cables for that. So I've actually gone to bicycle shops and buy these Bowden sheets. Oh, wow. Yeah, bring it back to the lab. It's a lot of, it's really engineering, right? You have a problem and you try to scavenge things from everywhere and then see what you can come up with. Let me see if there's anything else. I don't think so. Another thing that we sometimes use is we repurpose things that are already out there. So instead of designing the whole thing from the ground up, you might not really need to do that. So you can just repurpose an orthotic device. So how when you have when you sprain your wrist, for example, you can buy these things at Guardian or these shops, right? That it's just splints for the wrist.
Mm-hmm.
So imagine like a more complex version of that, but for the elbow or for the knee. Actually, you see also a lot of that, right? These structures that you put around your knee in order to help you out. So you can actually use those things as well. Just repurpose them for your needs. Just instead of deciding to design the whole thing. I mean, these things have been designed already by people that have studied and prepared these devices for many different sizes and applications. So you can just decide, oh, okay, there's already this structure that I can put around my elbow, and it helps the elbow move in a certain direction. Why don't I just go there and use that as the base, or to which I attach all of my cables or bladders if you're using pneumatic actuation, right? So that there's a lot of repurposing happening
sort
as well.
Of avoiding to reinvent the wheel.
Exactly.
So now we need to get into the outlook and
Yes.
future.
Where are we going with your field? Actually, you mentioned something really interesting, which was about gamifying how you do things. Instead of you looking at moving a cup from one place to another, you look at it from a game perspective. And I was wondering whether that approach interfaces or uses virtual reality at all.
Oh, it definitely can. Yeah, there's a lot of research going on about that as well, using like Oculus Rift and all these virtual reality glasses that you can get, and nowadays very cheap. Also, anybody can buy one.
Okay.
Yeah, you can use that. Of course, right now I don't think there's really like a widespread take of this. Also because if you look at it from a research perspective, it's not easy to prove that one certain way is better than another, right? So how do you prove that virtual reality actually like is better than just a normal game with a screen? And I'm sure from a company's point of view, you want to reduce costs as much as possible, and probably installing or like in investing a lot into virtual reality might be more costly than just using available tools out there, available games. But I do know that there's a lot of research going into that as well. So creating custom made scenarios where you can use virtual reality, and you instead of actually, for example, using the cup on the table, you might be grasping a fake object, so you're not actually grasping anything, and you have the robot delivering certain forces. So that's called giving haptic feedback, right? To make you feel that you're actually grasping that object. So literally all you would need for that is just the virtual reality equipment and the robot. You wouldn't need to be in a certain dedicated environment for that. So I think that's also why it's appealing, right? Because it's a lot of the devices, I mean a lot of the components of this system are already out there.
Right.
Just the glasses, and the computer. The problem is the robot. It's that's the one that
it's where you come in.
Exactly.
So I was just wondering, extending this a little bit, you've talked to us a lot about how these exoskeletons or exosuits are being used to help patients. And I'm wondering whether it can be used for normal people, and how can it be extended in that direction? Can we use these exosuits for pleasure, whatever that would mean?
Yeah. I mean, that's also one of the big debates, right? Which is on the more ethical side, which is, who should be wearing these things? Who should be using these things? Should it be just people that are impaired? Should we use this only for that? And how do you even draw the line? What's impairment anymore? Like, how do you define it? I think that eventually that's going to happen. Everybody's going to be able to just buy a device, buy an exosuit or an exoskeleton that will make them stronger, and they'll be able to climb a mountain in no time. Right? It's actually one of the biggest researchers in the field. He also he's a prof from MIT, and he first started in the field. He was, a normal person like any of us, but then one day he had an accident climbing. So he fell and he lost both his legs. I believe to frostbite, if I'm not wrong. And he, at the time, if I'm not wrong, he was already working with assistive devices, wearable robots, and prosthetics, especially prosthetics. So he became his own test subject.
Right.
So he uses the robots on himself. He actually, whenever he gives presentations, you can also see like that he has the legs, right? The metal legs.
Right.
And I first heard about this actually when I was seeing a documentary about this, about what will be the impact of having all of these technology available to everybody, because you might have people that purposefully chop off an arm in order to put another one, right? But again, I mean that's a bit of a maybe a different direction, because those are prosthetic devices. But I think it can be very helpful, right? It doesn't have to be just for people that have disabilities. It can be used in I mean, I'm not in any way in favor of like military movements, especially nowadays with what's happening. But it is very used in that capability as well. That's actually one of the main concerned parties, one of the main stakeholders in these fields is military. Like the U.S. military, they invest a lot of money into exoskeletons that their soldiers can use to become faster, stronger, to be able to carry more things. To be able, for example, in rescue missions, right? If you need to go and recover somebody from like a building that has collapsed, it's very difficult to move all those things around. You can have a guy equipped with these robots that can carry the stuff out of that place in no time. Another situation that you can use robots is in space also, because astronauts, for example, they have to deal with they have to interact with the tools, and they have to perform actions that they're not at the same level as it is here on Earth, right? Because you have to wear this suit. It's very uncomfortable. You can't feel very well what you're doing, and you're not as strong, because there's a big difference between your skin and the actual object that you're touching. So there are also a lot of research going in that direction, using wearable robots in space to help you perform whatever it is that you need to do there. And the other scenario that I mentioned before is in industry applications, right? So in warehouses, where people have to move boxes all day, every day of the week. And actually, a lot of people have problems because of that. They're the so-called work-related musculoskeletal disorders. And it's a huge problem. A lot of injuries related to work accidents that they didn't have to happen. And not only accidents, but also long-term problems. People that have to go down and up a lot of times, they end up with terrible back problems. That could probably be helped with robots. That was actually one of the robots that we were working in my lab. I wasn't the main engineer involved in that. It was another person that's no longer there. But it was a robot that was meant to help workers in factory scenarios to lift heavy objects. So, and it was very simple. Actually, it's a perfect roundup of all the things that I talked about. So it was repurposed orthotic devices that they were placed around the elbow, with a cable connected to that device, and then with a motor stored on your back, connected with Bowden cables. And the whole casing on the back was 3D printed. And then this cable just pulls, it's attached to the dorsal side of your forearm. So when you pull the cable, your elbow flexes. So you had two cables, two motors attached to each forearm, and it just pulls the arm up. And the cable is not connected directly to the arm, but it's connected to this brace that is around the arm. So that was one of the projects that we had in collaboration with industry. So there's clearly also interest in moving into that direction, trying to support workers. It's not just patients. You want to prevent people from becoming patients, right?
Okay.
Now, you mentioned the very beginning humanoids, right? Humanoid robots. Is there like an interaction between those researchers who are strictly working on, humanoids and your group and your area of research? Because they're not trying to help other humans, right? They're just trying to build robots.
I am not sure. I don't know if there's any direct interaction. What you would have is... So what I've seen of, and the thing that I think of first is collaboration with robots in performing certain tasks. So that's more on the human robot interaction side of things. So instead of having, for example, in this industry scenario, right, in the factory scenario, instead of having the worker wearing a robot that will give him more power, it's beneficial from the point of view of the worker has better control of what he's doing, and you're just giving more strength. But it's not that easy to use these robots, and they're not widely available yet. So what you also have is a robot that's a separate entity from the worker, and that robot will help the worker in performing certain things, like, for example, lifting a heavy table, something like that. So you have the robot on the other side of the table, and then you lift the table. You can guide the table to put it in a certain position, but the robot will be doing most of the heavy lifting. So you are there just like to align things. And I'm sure there are many other applications where you can do these kinds of this kind of paradigm, right? Where you use the robot to do things that will most likely hurt you, like lifting heavy objects, but you use the human's fine motor skills in order to control what the robot is exactly doing. Yeah.
All right. Thanks, Bernardo. So that will kind of wrap it up for us in terms of what research you do. Right now, we want to go into you, the human being outside of the lab. What gets you excited, and what do you do?
What do I spend my time doing? Before the pandemic, right? Because I feel like for many of us, there's a pre-pandemic identity and the post-pandemic. I used to go a lot, like music concerts. I'm very much into music. And even before coming to Singapore, actually mostly before coming to Singapore, because I find that the music scene here is not as like vibrant as I'm used to, so I kind of lost a little bit of that side of it. But there's still a lot of cool things happening, of course, and so I like playing instruments. I play the guitar. Just before I got to Singapore, I bought a drum kit. That was a bit of a dumb decision, but I don't mind because my brother uses it nowadays. But yeah, I'm super into music. I'd say probably that's the biggest thing that I do outside of the lab. And I've also tried to think of ways that I could use that more in my like professional life. How can I use music maybe in a more robotic scenario? And maybe a virtual reality kind of scenario where you have to play an instrument, maybe play the drums, but use a robot to help you. I don't know. There are many interesting things, I guess, that you could do with that. Because I find that music really, it brings... Not only does it bring people together, but it just like it opens something in you, right? So if you could use that power that music has over humans, it sounds like music is an alien. If you could use that power that music has on us to maybe motivate you to use better these wearable devices, or to motivate you to do better rehabilitation, I think that could also be quite cool.
You mentioned something interesting. So I know like playing an instrument has to do a lot with muscle memory, right? You practice like a gazillion times until like now it's just in your muscles and you don't even have to think about it. Do you think wearables can help in this area? Is that something achievable with wearables?
With wearables, to be honest, right now I don't see it happening yet. It's because we're still at the level of helping a person open and close the hand, like in a good way, in a way that you can do it a million times and it's not going to fail. Of course, not all robots are at that stage. Not all exosuits or exoskeletons are at that stage. You have many that are able to, for example, close just one finger, or close the next finger, the next finger, the next finger, right? So you have a sort of individual control there. But the problem there is the more individual and like fine motor skills you want to use to support, the more motors you're gonna have, the more complicated your system is, and it just doesn't. It's not feasible at the end of the day. If you want to have a wearable robot that's gonna help you in doing activities, generally you want something that's simple. It will help with simple tasks. Fine motor skill, it becomes more difficult. So maybe you would want something that's wearable but maybe not portable.
But what about like in 50 years, for example?
Maybe, yeah. There's a lot of research going into these like extremely or ultra light actuators, right? That like how do you call it? Shape memory alloys and stuff like that. So maybe you could use something like that, where it's very, very lightweight, so it makes no difference to have 1 or 20 of these actuators on your body. But right now, those devices are not able to create they don't have the properties that are needed. They're not as strong, basically. But what I have seen, which is pretty cool, this is quite a different side of research. It's using assistive devices still, and in a way a wearable robot to help a person play the piano, but by giving an extra finger. So this is inspired by it's really interesting. It's inspired by a family. I think it's a family or maybe a group of people in Brazil that they have this gene that it's very likely that a person in that pool of genes will have an extra finger. But it's not like an atrophiated finger. It's a full finger that they have the same exact motor control as any of the other fingers. It just looks like an extra index between the index and the middle finger. So you have this family of people. It's normal for them. And there's this particular researcher in Imperial College, and he does a lot of research on this, on understanding like how do these people control this finger? Because they are human, we are human, obviously, but we common mortals that only have 5 fingers, we have to go around our life using only 5 fingers, and they do exactly the same things with 6 fingers. So does that mean that you could add an extra finger to a person that has 5 fingers and still be able to control it normally? And where do you stop? Like, how many fingers can you add?
Interesting.
So this guy, this group there at Imperial, because for a short while I was at Imperial, they had this project that was a guy playing piano with an extra finger that you could actuate with your leg. So you would press a button with your foot, and then that finger would press. This is a very primitive way of using it, but yeah, I mean, maybe you could use these kinds of devices, for the guitar as well. Have an extra finger for those really difficult chords that you cannot reach. I know I found myself sometimes thinking, I wish I had like an extra arm growing out of my arm to help,
Sure.
Yeah. Outside of that, I play sports.
Football, right?
Football. We've played together many times, right? Now, fortunately, we're able to play again with the restrictions easing. I love tennis. I've played tennis all my life, but unfortunately now I haven't really been able to do it because you guys know how the research life is. There's only so much time that you have. If I want to do research, play football, play music, play video games. I also play a lot of video games, maybe more than I should. That's difficult. Yeah, but I think for some reason lately I've been so invested in tennis that I follow like almost every tournament that happens worldwide. Yeah, it's kind of a thing that runs in my family. My dad plays tennis. My uncle plays tennis. I mean, recreationally, obviously. My brother was very good at tennis, but then he became also a nerd like me. Yeah.
Well, it's been a pleasure having you here. Thank you very much for coming on.
Yeah, thanks a lot. It was a lot of fun. Yeah, thanks a lot. I did listen to a few of the episodes before, and I found it fascinating how people can talk so long about their field, and it's all so interesting as well.
All right. So thanks, Bernardo, and this is the end for today's episode. We'll see you again next time.